Good afternoon, everyone. So I'm from in the International Institute of Information Technology in Hyderabad, in India. And in our group, we basically work with dielectric elastomer actuators, which is again like gaining popularity for applications in soft robotics and soft actuators, particularly because of the fact that you can make them in thin film, and certain other things. For example, that they're inherently stretchable. They can be transparent if you do the electrodes right. So a lot of advantages are there. So we're basically looking at a simple flapping wing application for as a test of our DA fabrication strategy. But when we look at characterizing it, there are still some sort of gaps in literature where we basically started going into and sort of figuring out what can be done. So I don't know if just as an introduction to DEAs, I mean, if you don't know what that is, a very simple explanation is that it's a capacitor that has an elastomeric dielectric, which means a dielectric that is soft. And if you basically then actuate that capacitor, what ends up happening is that there is a stress that is introduced in the dielectric, and because of that stress, it begins to move. And it's not that it happens only in dielectric elastomers, or it can happen in any elastomer, normal ceramic elastomers as well. It's just that we don't notice that stress in normal capacitors. But if you make the elastomers, make the dielectric soft enough, you can experience that stress in the form of actuation. And if you're clever in designing either your electrodes or the way some certain constraints are there on the thin film, you can actually make them actuate in a specific way. And this has of course been been reported as well. For example, I mean, if you want, you can broadly divide the DEA world into two categories, where they're basically used as a power sort of an engine, and some mechanical constraints later, you can basically get the actuation you want, or you can actually use them as the actuator itself, and get some things to be actuated or moved. So in our case, we were actually looking at this kind of a system where we can actually use the thin film itself as both a structural component as well as an actuation component, and or actuation engine. And specifically, we are trying to model what can happen if, for example, if we have these kinds of actuators, what kind of actuation frequencies we can get, what kind of powers, efficiencies and per actuation we can get for these systems. So the way we went about it is that we fabricated these using a urethane polymer with a photo initiator, and they're basically spin coated and then UV cured to get the thin film. And on that, we basically put like a CNT electrode thin film, which is basically masked using a PET shadow mask, and that PET shadow mask is made using laser cutting. And we have to basically typically repeat this process for multiple, I mean, at least for 2 layers. If you're doing, like in this case, we're basically making a top flapper. So for the top 2 electrodes, we had to at least repeat this process twice. And, of course, at the end, if you want a specific kind of actuation, like I said, you have to do some kind of physical constraining. So in this case, we did that constraining by overlaying a stiffener, which is again like a PET thin film, which is stiffer than the elastomer itself. And we were able to get the final system done. So, and that's about it. I mean, it doesn't require a clean room. It requires a clean lab, but not an actual clean room. The reason I said a clean lab is because these, I mean, the way when we fabricate them, they actually break down a lot. So that is one of the major problems, like when you're spin coating multiple layers, and even if there's a tiny particles anywhere here, the amount of voltages that we are applying, the fields that we are applying, it can actually break down pretty quickly. So that's one of the sort of the dirty secrets of DEAs. This is one of the things that worked, and there is 100 others that didn't. But the one that works pretty nicely. I mean, if the video will work, I can show you. Yeah. So it feels like, you know, you're trying to twitch somebody's muscles. I mean, that's what we're going for. It's like we're trying to make it into an artificial muscle. And you know, so there are these two electrodes here. This is just an acrylic support structure. That is nothing to do. There's just two wires coming around here, and these are the actuators. Again, the other thing you know that is there about DES is that they actually operate at a pretty high voltage. Right, the electric field is very high, although the currents are pretty low. So in terms of power, it's not that much, and that is one of the studies that we are basically doing in my lab right now. And you can actually see that it's in terms of the actuation frequency as well, that amount of time it takes for it to actuate actually looks like a muscle. Okay, so that is what we were interested in this paper. At least we were trying to figure out what kind of frequencies we get, and of course we have to first like normalize displacement and, you know, figure out how to calculate displacement and everything. So we basically did this study where we had this, you know, the flapping wing sort of you know, characterized for how much displacement we are getting at what you know, applied voltage. And we were basically then we figured out that we are getting something like close to 0.5 body length. Body length in this case is 4 centimeters, like the length of the flapper. So that is how much we are getting at around 2.5 volts k-volt static. And after that, typically it breaks down. I mean, we saw the breakdowns of the order of 3 kilovolts for this particular thickness of the elastomer. So once we are able to do that, we are able to get a specific static thickness or static displacement. We basically wanted to see what kind of dynamic characteristics or you know, response we get from this actuator. So we basically looked at resonant frequencies for between 1 and 10 hertz, and at different you know, actuation voltages. And what we found is that it definitely resonated at a specific frequency, in this particular case 4 hertz. And one of the problems with DE is, again, we are happy about the fact that it's resonating at some point or whatever, it's giving us some displacement. But if you look at the runoff for this curve, that is also actually pretty significant. So it absolutely stops displacing at 10 hertz. I mean, it's one of those things that, I mean, if you look at it, I don't have a video of it right now, but it's like, it really tries to move, but you can see that because it's an elastomer, like the mechanical forces, the viscoelastic forces are sort of not allowing it to move more than 10 hertz, or actually not even at 10 hertz, even at 8 hertz or so, it kind of dies. But at 4 hertz, it's reasonable, and we're okay with that, because if you look at artificial, like if you look at your muscles as well, I mean, a simple experiment is you try to do this as fast as you can. I'm guessing you'll not be able to hit 10 hertz. So we are okay with whatever actuation we were able to get. So we were able to get a so frequency like a resonance at 4 and a subharmonic at basically 2 hertz. So that was an interesting observation for this particular flapping wing. The other thing is, like I said, we want to know what currents or what kind of power we are consuming for when you're basically switching, you know, one cycle of actuation. One of the easy things to do is basically just measure the current, that because it's a power supply that you are supplying with, you can just measure the current that it's giving out. Although, to be honest, there is some nitty-gritties to it. The power supply that we were using has a current output monitor at something like 8 hertz. And that's not enough at all to basically sample when you're charging a capacitor. So the way we did it is we actually put a series resistance in, and then you have to do a lot of juggling around it, because there is an isolation circuit and everything else to measure the voltage across it, because you're working at 2 kilovolts and you don't want to fry your laptop. But once you're able to do all of that, then you can measure it at something like 1 kilo samples or even 20 or 100 kilo samples. So If you do that, you'll basically figure out that it's just a capacitance charging curve. It basically, when you give it a voltage, it charges. I mean, it takes a lot of current, charges up, and then settles down. Where it settles down, and where this peak is are both interesting. Where it settles down is basically will give you the leakage current. I mean, it's a constant leakage current or leakage resistance of the entire capacitor. So that is also interesting in some cases. And the integration under the curve for the entire thing will give you the charge, which basically gives you the energy that it consumes. So both of these things we have analyzed as well. Particularly for, so let's say you actuate it for like 120 seconds. We basically take the last 20% as, let's say, subtle current, kind of arbitrary right now, but we are still studying what the best way of doing that is. And then you can basically see that, you can plot that current, settling current versus voltage, and, integrate everything else and call it the energy consumed per voltage. So that is what we have right now. We are basically now also looking at how much mechanical forces we are getting, and trying to see what kind of efficiency based on the input. This is the input power. Based on this, how much output we are getting, and we are trying to see the efficiencies as well. One of the interesting observations in this particular thing, like the current versus voltage, is that you would assume that it should be linear, because given that it's leakage current for the same capacitor, the resistance should be constant, which means the current voltage characteristic should be linear, but it's basically linear in two different paradigms. I mean, there's something happening at 1.6, 1.7 volts, where this is a specific resistance and this is a specific resistance that we're getting. So that's an interesting thing as well. We're trying to observe what those two paradigms are and why that is happening. No, that's all I have. Yeah. So that's all I have. If you have any questions, please let me know. Thank you.